The present lecture will be on Biot-Savart's law. The previous lecture, that is lecture number 2a, was on Maxwell's second equation of electrodynamics. In lecture 1a, we defined what magnetic induction vector B stands for, and it was emphasized that vector B, magnetic induction, was defined from Lorentz force equation, while in lecture 2a we described some properties of vector B, especially that its divergence is 0, which means vector B is solenoidal and which is indicative of the fact that magnetic charge or magnetic monopole does not exist. Earlier, we emphasized what current means, and we all know that this is the definition of current. I is dq dt. So, current is rate of transport of electric charge. Now, this transport or movement can occur in a wire or a filament or a line, or transport of electric charge can occur in a volume. So, there are two types of transports of electric charge that gives rise to current, either in a wire or filament or line or in a volume. Again, let us note that a wire has a length. So this is a wire, it has a length, an element of which is dr, and if A is the area of cross section, then if we take the product of A dr, we end up with an elemental volume d tau. So wire has a length as well as a volume. What does this mean? Actually, we are trying to look at the same phenomena from two different perspectives. Now, what is the phenomena? The phenomena we are discussing is a current distribution. We are speaking of a current distribution, and our way of looking at this phenomena, that is current distribution in a region, can be of two types or can be from two angles. One is current in a filament, the other one is current in a volume. So, we speak of two types of current distribution. One is filamentary current distribution, the other one is volume current distribution. In filamentary current distribution, we consider a wire or a line or what we call filament, an element of which is vector dr. It carries current I because dq charge moves in time dt along the wire. Now, current distribution in a wire is therefore described by a current element, and current element is defined as the product of the current carried by the wire and the elemental length of the wire. So it is I vector dr. While in case of volume current distribution, we say that suppose this is a volume denoted by tau, and in this volume charges are moving, and charges are moving means there is current. So volume contains a current due to movement of charges, and this current distribution in a volume is described by volume current density element, which is defined as the product of vector j and an elemental volume d tau, where vector j represents volume current density, which is actually current per unit area, and its unit is ampere per meter square. Now let us speak of a theorem which states that the two distributions, one was filamentary current distribution, the other one is volume current distribution. Now according to this theorem, these distributions are equivalent. Actually, that is what we wish to emphasize at the very outset. Now how is it? Let us consider the quantity J d tau. J represents current density, volume current density, which is, as we showed, which is I by A, and d tau is the elemental volume, which is actually product of A into dr, and on cancellation of A we are left with I dr. So J d tau is actually I dr. So this is the filament, and a portion of the filament has a volume which is d tau, while the length of this element is dr. Now charge moving along vector dr gives rise to a current, because flow of charge means current. So as charge is propagating through this length element, obviously it will generate a current, and this current is along dr because the movement is along this direction, so the current also is expected to be along this direction, and therefore vector j that describes this current will also be along this direction, it being a vector quantity. So it is ensured that vector j and vector dr are parallel, and therefore from this equality we end up with this relation: vector j d tau is equal to I vector dr. So we re-emphasize that vector j d tau, which corresponds to volume current distribution, and I dr, which corresponds to filamentary current distribution, are in fact or are essentially equivalent. Both describe the same phenomena, namely a current distribution. Let us elaborate a bit on this. Consider a volume tau, and here charges are moving, charges are in motion, and current in this volume is described by volume current density vector J. Now what is the mechanism of generation of current here? The mechanism of current in this volume tau is that charges are in motion. So the charges, say any charge q, it follows a particular path. So this is the path it follows. In other words, it moves along a particular circuit, and movement of charge corresponds to current, means a current is being flown along this circuit, and a small portion of this circuit is dr. Suppose this is the jth circuit, this is the first circuit C1 along which some q is flowing, C2 is another circuit along which another charge is flowing, C3 is another one, the third one, along which some another charge is flowing, and so on and so forth. And similarly we have the jth filament. So the idea of filament is therefore inherent in this current distribution, which is essentially a volume current distribution. So actually what we have emphasized is that the volume current distribution can be looked upon as multitude of filaments. So it's a multi-filament current distribution which gives rise to a volume current distribution, and therefore there is actually no difference. It is just how we look at the things. So in view of this, we can write this equation which corresponds to filamentary current distribution. Here we spoke of the jth path, jth circuit, of which drj is a small element carrying current ij due to flow of q through the cj, which is the jth circuit, and therefore we have the quantity ij drj. And if you integrate over all such small elements with which the cj circuit is built, then you get this integration sign over cj, and then you sum over all such circuits, first circuit, second circuit, third circuit, and so on and so forth, to end up with this expression. And this is equivalent to a volume current distribution, which is actually an integration of vector j d tau over the entire volume. Now let us emphasize another thing, is that, and that is, we are dealing with source quantities, and therefore we can attach primes. It is customary to indicate source quantities by attaching a prime symbol, and the field quantities are in general not attached to any prime. So they being source quantities, I is a source quantity, j is a source quantity, and so on and so forth. And therefore let us rewrite this expression to get this expression, which is equivalent to this one. Here the volume current density is a function of source coordinate, and d tau prime is the source volume element, while ij prime is the source current, drj prime is the source vector element, line element of the source circuit, cj prime, and we are performing sum over all such j's, all such circuits. So the equality is explained and established. And another thing is that here we considered so many circuits, so many charges are moving, and therefore we had to do this sum. Now to make things simple, it's often easier to deal with one circuit. To make things simple, therefore we just do away with that summation sign and consider a single circuit, and we can claim that it is equivalent to the volume current distribution. Next, let us discuss about the force which a current element experiences when it is placed in a magnetic field. So let us consider a filamentary distribution of current. This is a conductor denoted by C, and it carries a current I. Vector dr is an elemental portion of the conductor. A is the area of cross section, and let me repeat once again that this conductor is placed in a region where there is a magnetic induction of amount vector B. IDR is the current element. Now current is flowing in this circuit. This means charges are in motion and they are moving with some velocity. So it is expected that this vector dr, which is the line element, would be parallel to the velocity, or in other words, put in another way, the charges are moving along vector dr, and therefore we have a current along this direction. So we can take that, we can say that vector dr is parallel to the velocity vector v. Now in this length element, in this line element, how many charges are there? How many charge carriers are there? This is the first task which we will address. So number of charge carriers inside this vector dr, inside this line element. So number of charge carriers, let us try to construct an equation. So number of charge carriers is equal to, we write it again, number of charge carriers per unit volume, and then multiply it with volume so that both sides remain same, because this is volume, this is volume. Now how is this volume? Cross section is A. If you multiply it with dr, you get this amount of volume. Now number of charge carriers per unit volume is just the number density, which we denote by n. So it is actually n a dr, a being the cross section and dr is the length element. So number of charge carriers inside vector dr is n a dr. So this is the picture redrawn. This is the volume a dr, this is area of cross section, this is the length element dr, and in it how many charge carriers are there? There are n a dr number of charge carriers. And what is the charge that flows through this portion? And that is the number of carriers within it multiplied by the charge each one carries. So the number is this one. If you multiply it with q, which is the charge carried by each carrier, then we get the total charge dq, which flows in time dt through this volume ADR. Now the Lorentz magnetic force that these charge carriers experience, they carry a charge, total amount of charge that flows through here is dq, and this one is placed in a magnetic field B, which means these dq charges are acted upon by a Lorentz force exerted by the B field. So this is the Lorentz force. We did it in lecture 1a. Here q will be replaced by dq, which is an elemental amount of charge, and therefore the force that dq experiences will also be elemental, which we prefer to denote by vector df. So just let us rewrite this equation in this way. Instead of f we have df, instead of q we have dq, and v cross b, here also v cross b. Now v is dr dt, and therefore dq dt is there, which is just the current. So we have got the final expression, and that is vector df equal to I dr cross b. So what we have actually done and what we have actually got is this. There is a region where a magnetic field is effective, denoted by vector b, and in this region we have placed an IDR, a current element, and this current element therefore experiences a force due to this B field, and the amount of force, the elemental force is df equal to IDR cross B. So this is the result which we got. Now what is the current flowing through this circuit? The amount of current is I equal to dq dt, and the value of dq we derived to be na drq, and therefore put it here to get the value of current as nqva. V here comes from this ratio dr dt. Dr is in dq, which flows in time dt, so dq dt gives rise to dr dt, that is a velocity. So this is the current I that is generated due to flow of dq in time dt through this circuit, which is placed in a magnetic field B. Now let us go back to this one again. This is the elemental force experienced by this elemental length dr, or current element IDR. So being in a magnetic field, the entire circuit of which IDR is a part. So this entire circuit will also experience a force which can be obtained by integration over df, and that we have done here. So vector f is just you integrate over df, and therefore we get this relation. F is closed integration over C IDR cross B, closed because the circuit is closed. That is what we have taken. Now this result holds for filamentary current distribution because we have considered the current to flow in a wire or a filament. So this is a result which can be attached to a filamentary picture. Two things are to be seriously noted. Earlier we said that current produces a magnetic field, but here you have to be very careful and not to confuse that this B is not produced by this I. Actually, IDR, current element, is placed in a B field. So IDR did not produce B. That we have to make clear. This B has been produced by some other external agency. So IDR is not the source here. Rather, it is a field circuit element because it is present in a magnetic field B, which it did not create. So IDR is not the source of B. Now, this is the result that holds for filamentary distribution. So what is the result for volume current distribution? And that is extremely easy to attain just by the switchover technique. And the switchover technique is, as we did as a part of a theorem, that we have to replace IDR of filamentary distribution by vector j d tau, and then we will get the corresponding result for volume current distribution. Now here we have df equal to IDR cross B, so instead of IDR we will put j d tau to end up with this result, j d tau cross B. So this is the elemental force, and if we integrate over volume tau, then we end up with the total force. And obviously there will be no circular sign because a volume is always closed, but for a closed circuit we have to put a circle sign. We now move on to our main topic, namely Biot-Savart's law, a law that was enunciated in the year 1820, in the same year in which Ørsted observed that current produces a magnetic field. We should be careful about one thing. The magnetic induction vector B is defined from Lorentz force equation as mentioned in lecture 1a. But what is the expression of vector B, that is the explicit expression of vector B or the form of vector B, was given by Biot-Savart's law. So Biot-Savart's law does not define vector B, but it gives what look this vector B will have. So B is defined from Lorentz force equation, and the explicit expression of vector B is given by Biot-Savart's law. Let us first consider a filamentary current distribution as shown in the diagram. C prime is the source circuit carrying current I prime, which is the source current, an element of which is I prime dr prime, I prime being the source current, and I prime vector dr prime is the source current element. According to Ørsted's observation, current produces a magnetic field, and therefore this current element, this elemental current element, will have its influence in the region surrounding to where it is placed, in its neighborhood. So this will produce a magnetic induction at a point P, and this expression was given by Savart's law to be of this shape, where vector r represents the field coordinate, which is the position vector of the field point with respect to the origin, the position vector of I prime dr prime being vector r prime, and the position vector of the field point with respect to the source point is vector r. We can see a triangle here, and we can apply the triangle law of vector addition, from which we end up with this relation. So let me mention once again that the position vector of the field point with respect to the source is capital vector R. And this capital vector R, being a vector, it has two parts. One is the magnitude part, which is given by this one, this expression, and the unit vector part, which is given by this expression. So let us now come to the Savart's law. I prime dr prime is an elemental current element. It's a current element, and therefore the field or the magnetic induction that it produces at field point P will also be elemental. And this elemental magnetic induction has this structure, where this cross stands for the cross product. So if you remove it, you have to replace by a sign, and of course the resultant direction will come into play. So this is the elemental magnetic induction as suggested by Savart's law in 1820. In Coulomb's law, we found a proportionality constant in electrostatic class, and that proportionality constant was 1 divided by 4 pi epsilon 0, where epsilon 0 was permittivity of free space. Here too, the elemental magnetic induction that is produced, elemental magnetic induction, its expression also contains a proportionality factor in SI unit. It is mu 0 by 4 pi, where mu 0 has the value 4 pi 10 to the power minus 7 Henry per meter and is called permeability of free space. The I prime dr prime, as we mentioned, was an elemental current carrying agent, and it is a part of a greater circuit. In this diagram, we have taken it to be a closed circuit. So if I prime dr prime produces a field or magnetic induction at P, then the circuit also will produce a magnetic induction here, and the effect of the entire circuit can be obtained if we integrate over the circuit. So the circuit is made up of several such I prime dr primes, and therefore we can just integrate to get the total effect of C prime at P. So due to the entire source circuit C prime, which in this case is a closed circuit, the magnetic induction at P is given by this expression. Here we have used the integral, closed integral. Now Savart's law involves an r cap by r square, so we can just multiply the numerator and the denominator by a scalar r, and if you do so, in the denominator we have r cubed, and in the numerator we have r into r cap, which is the resultant vector r, which is the position vector of the field point with respect to the source point. And if we write down explicitly, then we end up with this factor. So this is Savart's law. One thing is very clear from this expression. In the right hand side, in the integrand, we have two types of coordinates. One is small vector r, which represents the position vector of the field point with respect to the origin, and a vector r prime which is the position vector of the source point of the current element with respect to the origin. So we have two variables in the integrand, but integration is performed over all points of the source circuit, which means this r is not affected, but this r prime is affected. At this point this is r prime, but if you shift it to a different value, then r prime will vary. So we are integrating over r prime, and therefore after integration, after all points have been taken care of, have been counted, we no longer have any point left. So after integration, naturally r prime will not occur in the expression of b. But since we have done nothing to this vector r, so after integration the magnetic induction vector will contain vector r. In other words, the magnetic induction is a function of field, and we call it a field function. The expression which is written over there corresponds to a filament, and therefore it is called a filamentary current distribution by Savart's law for filamentary current distribution. Now what if instead of filamentary current distribution we have a volume current distribution? Then instead of a filament we have a volume, an element of which is d tau prime, which has position coordinate vector r prime with respect to origin. At vector r prime, the value of volume current density is vector jr prime. So vector jr prime d tau prime is equivalent to I prime vector dr prime, as we did earlier in the switchover formula. So in the filamentary current distribution of Biot law, we have to replace I prime dr prime by vector j d tau prime, and if we do that we get the elemental value of magnetic induction in this way. And if you integrate over the entire volume, that is, we consider all d tau primes which make up tau prime, then we end up with this expression of magnetic induction. The integrand contains vector j, which is a function of r prime, so j is a source function, but after integration over the entire volume, integration over all the points, we end up with vector b, which definitely doesn't contain any vector r prime. So it is only a function of vector r, as we said here. So this is filamentary distribution, Biot law for filamentary distribution, and this corresponds to volume current distribution. So this is Biot law for volume current distribution. The next question that appears to everybody's mind is, what are the applications of Biot law? We'll discuss the applications in the next video named 3b, but let me mention the cases in a nutshell. Consider an arbitrary plane curve AB. A and B are the extremities which make angles theta 1 and theta 2 at P, which is the field point, which is also called the pole of AB, which can be taken as the origin with respect to this reference line. So the question is, if this arbitrary plane curve carries a current I prime, what is the magnetic induction created or produced by it at some point P on the same plane? That we can find out exploiting Biot law. If we have a circle which carries current I prime, then what is the magnetic induction that this I prime creates at P? We'll address this. Also, we'll address the case of an ellipse which carries a current I prime, and the field point is taken to be one of its foci. So what is the field produced, magnetic induction produced by this I prime here? And similarly, if we consider a parabola, this is a parabola, current coming from infinity, and it turns over along this line around this focus, P is a focus, and then goes to infinity once again. So what is the effect of I prime at P? The effect was observed by Ørsted, and the form of the magnetic induction created by I prime will be obtained from Biot-Savart's law. If we have a semicircle carrying current I prime and P is the center, what will be the magnetic induction at P? A very important and oft-used problem is that of a straight conductor or straight wire which carries current I prime. It is oriented along the z-axis, and suppose field point is P, rho phi 0 is its coordinate, z is 0. Then what is the effect of this current at this point in terms of production of a magnetic induction? That can be discussed in the next lecture. If we have this type of a current distribution where we have two straight lines and two arcs, then we can find the magnetic induction at P, where P happens to be the point of intersection of the two straight conductors extrapolated. If we have a square loop, what will be the magnetic induction at the center? And in a similar way, if we have a hexagonal loop, then what will be the magnetic induction produced at the center of the loop? All this can be addressed using Biot-Savart's law. It's time to wind up the discussion. Let us make a gist of what we gained from this lecture. B was defined from Lorentz force but expressed using Biot-Savart's law. We also studied at the beginning that there is a technique to switch over from filamentary current distribution to volume current distribution, or the other way around, where we can switch over from volume current to filamentary current using this theorem. We also derived the elemental force that a current element I vector dr experiences if it finds itself in a magnetic induction B, and the total force, the expression of which was also obtained. And we also derived their counterparts in case of a volume current distribution. The number of charge carriers inside an elemental length dr was obtained to be Na dr, and the current that flows through a circuit element was derived in terms of the number density of charge carriers, the charge carried by each carrier, velocity of the charge carrier, and the area of cross section of the conductor. In course of our discussion, we came across the name of certain very famous people, namely Biot, Savart, Lorentz, Ørsted, Henry. And in a subsequent lecture, which I will call complementary lecture 3b, we'll discuss a bit about them, as well as we can address certain queries and we'll discuss certain problems. Let me end this lecture with this quote. It is the mark of an educated mind to be able to entertain a thought without accepting it. It was a statement of Aristotle, the famous Greek philosopher. So every new idea or every new thought, every new approach should neither be rejected outright nor accepted at face value. Rejection or acceptance, whatever we do, should be done after verification and not under any duress, pressure, bias, or intimidation. Thank you.